Hey, welcome back to Calculus. In this video lecture, we're going to take a look at the last section that we'll cover in Chapter 10, Section 10.4, and I want to show you how you can calculate the area of regions that are bounded by graphs of polar functions of the polar angle. All right, so the two goals of the lecture are written there at the top. I want to show you how to describe the regions that we're going to be calculating the area of, and then I want to develop an integral that can calculate the area of those regions. We'll do several examples, sometimes me leaving the actual integration to you to keep the video a little bit shorter. So we have to start by deriving the area for a formula for the area of a sector of a circle. Here in figure 1, you're shown a sector of a circle. A circle has radius r, and the sector is subtended by an angle theta. And to derive a formula for that, what we need to remember is that the area of that sector, which I'll just denote by A, would have the same proportion to the area of the whole circle, which is pi r squared, that theta would have to the angle of the whole circle, which is 2 pi. And if we solve that for A, I'll let you check my algebra, that we get that A is 1/2 r squared theta. So that's the formula for the area of a sector of a circle. It's going to be kind of the analog of a rectangle when we were doing our integrals in rectangular coordinates. Okay. So in second figure down here, we've got a region R. It's labeled R there. If you can zoom in and see it, I took these figures from your book. And that region R, every point in it, its theta is between two values. The book calls them A and B. I'll call them the same. You can see those here. I'll just outline them as we talk. That's the ray theta equaling A. This is the ray theta equaling B. And then between those, any theta value between A and B, the radius is bounded below by 0. You can see that in the picture, but it's bounded above by the graph of the function, f of theta. So if I picked a theta between A and B and I start drawing that ray, the radius has to stop when it gets to f of theta. So this describes that region R. Okay, so that'll end up kind of playing into our limits of integration and so on. So that's the area I'd like to calculate. That's our goal. If I restate it, find the area of R. All right, so that's what we're trying to do. So let's look at the third figure. Scroll down here a little bit. So in this third figure, what has the author done? It's taken the interval from A to B, the theta interval from A to B, and subdivided it into a bunch of subintervals. So that sounds kind of familiar. Yeah, so we take the interval from A to B and we subdivide it. We start off with A, we could call that theta sub 0, and then we pick a theta sub 1, and so on, until we get up to, say, theta sub n, which would be B, and those are equally spaced angles separated by, say, something called delta theta. You can see the delta theta label in the picture here, so it's the width. Yeah. So because the curve f of theta is not a circle, that little blue shaded region in figure 3 is not the sector of a circle because the radius is changing. But if delta theta is small, we can approximate it with the sector of a circle. So if we make our local estimate, remember returning to our theme of local estimates when we're thinking of integrals, our local estimate for that area, well, it would be 1/2 the radius, because I'm thinking of that blue thing as a sector of a circle. And what's the radius of the sector of the circle? Well, I'll just assume that it's f of theta. In the picture there, he has theta, well, here I'll do it too, with a star and an I. That's just all the Riemann sum notation. So theta sub I star is some value of theta between theta minus 1 and theta, or I sub minus 1 and theta I. My tongue is not working this morning. Okay, and then I have to multiply that by the angle. The angle is delta theta. So that's our local estimate. That's the area of that little blue thing approximately. Yeah. If delta theta is small, it gets better and better. So if we added all those things up, then we would get an estimate for the total area, taking the limit as delta theta goes to 0. Can you see what the integral is? Maybe you can pause this and write this integral down before I do. It's going to be the integral. Well, the limits of integration are going to be a to b. And then that thing, that local estimate, tells you what we're integrating. It should be 1/2 of, excuse me, I forgot. It's f of theta squared, right? In the formula for the area, you have to square the radius. Sorry, it's too late for me to stop and remake this video, and I don't know how to edit, so you just have to deal with that mistake. But so I'm writing it correctly in the formula down here. I take 1/2 f of theta squared d theta, and I integrate that from a to b. Okay, so this is the main result that I wanted to derive. Make it look important down there. The main result is that to calculate the region in a plane bounded by a polar function, as the angle goes between A and B, every ray for theta between A and B kind of intersects that region once. So the region is swept out once as theta goes from A to B. To calculate the area of it, you integrate 1/2 f of theta squared d theta. So it's got this 1/2 kind of built into the formula. So you have to remember to put it in there when you're calculating it. Okay, let's do some examples. You can pause the video and look back, or if you wrote that down, I'm going to move that. Well, I can leave it up here in view while we do our first example. So I've generated some graphs here with Desmos, or actually I think I used GeoGebra. It doesn't matter, but I've got the graphs of the functions that I'm looking at are already drawn. So in our first example, I want to take f of theta to be theta, and I'm going to let theta go from 0 to 2 pi. So there you're looking at the graph of it. Here the polar radius is the angle. So I hope you've been thinking about the polar plane enough that that graph at least kind of makes sense, that as the angle increases, so does the radius. And in fact, they do it at exactly the same rate. So you end up getting that very pleasant kind of spiral shape. Yeah. So what's the area enclosed by it? Well, the area enclosed by it would be, let me start shading it. It's between the curve and the pole. So if you took all those rays, yeah, you'd end up getting a region that looks like this. It's a very interesting shaped region. It would be difficult to calculate the area of it in rectangular coordinates because things aren't graphs of functions and so on. You'd have to cut it up into a whole bunch of pieces. But that region is simple to describe in the polar plane. For every theta between 0 and 2 pi, the radius just goes between 0 and theta. Yeah, if you pick a theta between 0 and 2 pi, let me pick, say, this guy. This looks like theta equaling 5 pi over 6. That spoke. If I pick that theta, the radius can go from 0 until, well, f of theta, which is theta. Yeah. So all of those rays, just imagine them turning through the angle theta, and they would sweep out, quote unquote, that green region. Okay, so we can make quick work of calculating this area because I'm going to put the 1/2 in front. I usually will. It's the 1/2 the integral from 0 to 2 pi, and then I have to square my function, so it's theta squared d theta. Yeah. So this integral is elementary. We can just do it together real quick. It's 1/2 times 1/3 theta cubed from 0 to 2 pi. So that's going to be 1/6 2 pi quantity cubed, or if you prefer, 8/6 or 4/3 pi cubed. Cool. So there's computing an area with a polar integral. Let's do another one. Second example, I've drawn one of those roses. I hope you, in that activity from 10.3 part 2, I hope you got on Desmos and played around. It's not a surprise to you that with this rose with an odd multiplier 5, it has 5 petals. And what I'd like to do is calculate the area shaded there. So I'd like to calculate the shaded area. The area inside this rose, cosine r equals cosine 5 theta. So in order to do that, I'm going to take advantage of a little bit of symmetry. what I want to do, I wonder if I can, maybe I can blow this up to do this a little bit more carefully. Um, I want to calculate just the area, this will make the integral easier, of the part of this shaded area that I'm outlining in black right now. I'll just kind of hash it. Yeah, because if we could calculate that shaded area, then the entire thing is just some number of times it. Yeah, can you pause for a second and tell me how many times? Like, say, if I knew that black area, what would I multiply it by to get the area of everything? You can pause for a second. I won't pause. I'll just say it. I'd have to multiply it by 10. 10 of those things that I've shaded in black together would give the entire thing because there's two black shaded areas per petal and there's 5 petals, right? So the area is going to be 10 times that black thing. So what I need to do is describe the theta bounds on that black thing. I already know that R is bounded by a cosine of 5 theta. I can see one of the theta bounds. It's theta equaling 0, right? That's the lower limit of integration. But what we need to know is, well, what theta value is the upper limit of integration? What theta value is the upper limit of integration? When did that radius return to the origin, right? That's what we need to know, is that when theta equals this question mark value, then the radius has returned to the origin. So we have to use some knowledge about the cosine function to understand that. So we need, what is the first time that the cosine function takes on the value 0? Yeah, say starting with positive angles, or 0, I mean, the cosine starts off at 1, yeah, the usual cosine wave, and then it drops to 0 when the angle gets to pi over 2. So the first time that the cosine function is 0 is when its input is pi over 2. The input of our cosine function is 5 theta. So what we need to do is find out, well, how can 5 theta be pi over 2? Pi over 2 because that's the first time that the cosine will return 0. Okay, well, 5 theta is pi over 2 means that theta is pi over 10. Pi over 10. So that's the answer to my question, what's this theta value? The theta value right there is pi over 10, and that's my upper limit of integration. All right. So to set this integral up, how are we going to calculate the area? Remember, we wanted the area inside the shaded region. So I'm going to take 10 times that little black thing that I shaded there. And that shaded region would be the integral the integral 0 to pi over 10. This is what we just worked out. And then I take my radius, which is cosine of 5 theta, square that, integrated d theta. So if we clean this up a little bit, we get 10 times a half is 5. The integral from 0 to pi over 10, cosine squared 5 theta d theta. All right. So now we're lucky. We studied all those integration techniques in chapter 7, and we know how to handle this integral. The cosine squared, you do it with a trig identity. You remember that trig identity. It's 1/2. So I'm going to bring the half out front. It's 1/2 1 plus the cosine of 2 times the angle. Well, my angle here is 5 theta already. So 2 times it is 10 theta. Yeah. So there's my trig identity. Let's do one more line together. So we get 5/2. And now I'm anti-differentiating. So it's going to be theta plus the antiderivative of cosine of 10 theta should be 1/10 the sine of 10 theta. By a substitution, if you like, or just by that pattern. And then we need to evaluate that from 0 to pi over 10. Okay. So if I give myself some more room here, that's 5/2 plugging in pi over 10 for theta. I get pi over 10 plus 1/10. The sine of 10 times pi over 10 is pi. Minus plugging in 0 for theta, I would get 0 plus 0. The sine of 0 is 0. Sine of pi is 0. So we end up getting 5/2 times a tenth. And I already wrote the answer down here, so you can check it. I was going to leave this to you, but I ended up doing it. So it ends up being pi over 40. Excuse me. I don't think that that's right. I don't want that answer because what does it end up being? It ends up being 5 times pi over 20. Pi over 40, I think, is just the little tenth of it. So yeah, we get 5 pi over 20, and that reduces to pi over 4. Thank you, not pi over 40. Yeah, so 1/10 of that is pi over 40. Good. All right, so the area inside that rose, all 5 petals, pi over 4. Very interesting. Okay, let's do another one. This one I've already kind of wrote out the computation. I just kind of want to talk you through it. You're looking at a graph of this thing. F of theta is 1 plus sine theta, and I just graphed it with technology. You can do the same thing. You can graph it with Desmos. So the curve f of theta equals 1 plus sine theta looks like that. And if we just sort of mark on it a couple of theta values, the sine of theta is 0. So when the angle is 0, the radius is 1. That looks right. Looks like the point radius 1, theta 0 is on there. Then when the sine gets to say, or when theta gets to say pi over 2, the sine of pi over 2 is 1, and 1 plus 1 is 2. So in this pi over 2 direction, the radius is as big as it's going to get, 1 plus 1. But then once you enter the second quadrant, the sine function starts shrinking again. When the theta gets to pi, the sine is back to 0, so the radius is 1. And then in the third and fourth quadrant, the sine is negative. So we'll be subtracting something from that 1. So that's why the radius is getting smaller. When you get to 3 pi over 2, that's the angle that points straight down. The sine of 3 pi over 2 is minus 1. So the radius is 0. We're back at the origin, and then the radius slowly climbs back to 1. So that's kind of a way to think about this curve, 1 plus sine theta. All right. So using our formula from above, the area inside of it is 1/2 1 plus sine theta quantity squared. And I wanted to do this example for a couple reasons: to show you this curve, this cardioid curve, people call it. Um, and also to indicate that, like, sometimes when you square this out, so if I multiply out 1 plus sine squared, I get 1 plus 2 sine theta plus sine squared theta, and then I would integrate that term by term. Yeah, I would write that integral in three pieces. So I would integrate the 1, the 2 sine theta, and the sine squared being treated with a trig identity like above. So here, you can check me. Sometimes I work too quickly and make mistakes, but I'm going to claim that that integral evaluates out to 3 pi over 2. All right, so maybe one of you will carry out that integration and write me an email or send me a message on Canvas, or just tell me on Zoom whether or not you got the same answer. Okay, so one more example, and it illustrates how to find the area between regions. So a couple of the problems I'd like you to do will ask you to do this. So here I've drawn 2 polar curves. 1 plus cosine theta is the one that's kind of drawn in that purpley color. I can try to match it as I shade it. So the purpley color thing is 1 plus cosine theta. It's also one of these cardioid shapes. And then the one that's drawn in kind of the greenish color is just the polar function g of theta equals 1. And I've shaded the regions inside of both those. And what I'd like to do is find the area inside the purple one and outside the green one. So you can see that in the picture, what I'm trying to find. So we'll have to think of it as a difference of 2 areas. We'll take the area inside the purple one and then subtract off the corresponding area that was inside the green one to get what's in between. And what we're going to need to know is, well, what are these angle values? You can see what they are in the picture. Yeah, they look like they're equal to, well, this top one is pi over 2. The bottom one, 3 pi over 2, but when we describe these regions, remember theta has to go from some value increasing to another value. So I'm going to take this bottom angle not as 3 pi over 2, but minus pi over 2. because then every angle between those two things, every angle between minus pi over 2 and pi over 2 determines a segment in my region. If I just drew one of those angles, let's say it's this one, then the segment I'm talking about is that thing. Yeah. So can you imagine as theta goes from minus pi over 2 to pi over 2, those segments, I just drew one of them, would exactly sweep out the region in between those two curves. So those are going to be our limits of integration. How would you find those in general if you weren't looking at the picture, or if it wasn't so obvious that they were pi over 2 and minus pi over 2? You do the same old thing. You would set, you're wondering, when is f of theta the same as g of theta? Yeah, so you'd have to solve that to find these things. Well, that's if and only if the cosine of theta is 0. And the cosine of theta is 0. Well, it has infinitely many solutions, but among them, and the picture is guiding me to pick these two, the cosine is 0 at minus pi over 2 and pi over 2. So that's how you can kind of algebraically. So I'm picking those two of the infinitely many solutions to the equation cosine theta equals 0 because I'm looking at that picture. Okay, so then to finish this off, how do we set this up? Well, we need to calculate the area. And the area, I'm going to think of it as a difference. If I take the purple region first, I would integrate 1/2 minus pi over 2 to pi over 2 of f of theta squared. That's 1 plus cosine theta squared d theta. But then I need to subtract from that 1/2 the integral from minus pi over 2 to pi over 2 of g of theta squared. That is 1 squared d theta. And I can certainly rewrite that as a single integral. And if you want to, you can always use this as a formula. It's 1/2 the integral from minus pi over 2 to pi over 2. And then I got my outer function, if you like. I'm trying to use sort of familiar language, squared, minus my inner function, squared. Okay? So once again, in order to actually do this integral, I'd have to multiply that out. Right, so I have to expand out 1 plus cosine squared. So that's going to be 1 plus 2 cosine theta plus cosine squared theta. And I've got this minus 1. That's kind of nice. The 1 and the minus 1 eliminate each other. So we just have to integrate 2 cosine theta plus cosine squared theta d theta. All right. So here I'm going to let you take over. Oh, I thought I had written an answer down here, but I didn't. So I'm going to stop to keep the video short and won't carry out that integration. It's the usual. You have to find an antiderivative for cosine theta. You know it. Use that trig identity, 1/2 1 plus sine 2 theta. And you can meet me in a Zoom meeting or send me an email and tell me the answer. Okay, so you finish this. We'll talk. Okay, see you soon.